quick review before we jump to the quiz. No? So in the last section, we are moving to the sorting algorithms. You know that there's a lot of sorting algorithms in general. We just start with three stemless sorting algorithm. Okay, then purpose, selection, and insertion sort. Okay, and we know that all of them have the same complexities in, say, ON square. Okay, it means that in the worst case they have the same running time, but in general these algorithms will be different in the execution time because on average algorithms have their different properties. Okay, and we will see, we'll try to compare and see why one algorithm is better than the others even though they have the same complexity ON square. Okay, and in the last section we work with purpose sort already. We see the idea is that they try to move or compare two items and to check whether or not they are in the good order. Then if not, they swap it and they try to check the second pair like that. And after the first iteration through all elements of the array, we have something that we call an invariant. It means there's something that will be true for each iteration of the algorithms. In this case, we know that for each iteration, we will bring the, let's say, biggest item to the last position, the biggest item to the correct position in the sorted position. Okay, means that in the first iteration, we take the biggest value to the last position, and the second iteration through the array, we pick the second largest item to the second last position, and so forth until we do it in n time. Means that we pick n elements and put it in the correct order. Finally, our algorithm is finished because we already put n elements of the array in their sorted position. Then we have a sorted array. Okay, that is the purpose sort. And I just mentioned that the idea of we don't need additional space is quite important for some situations. You see, let's say if we have 100 gigabytes hard drive, if we try to sort, if we need an extra space in order to sort, means that if we have 100 gigabyte and we can only sort, let's say, 50 gigabyte because we need external space, additional space in order to sort. It's not good in that situation for sure. Okay, so that is one of the remarks you should remember. And we have the purpose sort is slow, but the idea is very easy to understand. And then we have the purpose sort. We see the simulation. Okay, and after the first pass, we know we try to analyze the situation and why we have n minus comparison. I mean, for sure, for all iteration we have it. For the first iteration we have it like that. For the number of swap, we know why we have 0 and why we have -1. It means in which situation. So 0 means we have the array in the sorted order already, so we don't need to swap anything. And for n-1 means that the first element is the biggest or the largest value in the array, so that we have to move them n-1 step back to the last position. Okay, and if we repeat that process, we have it. And finally, we have the algorithm here. Just say that is the algorithm. Say this is the, we say for each iteration we try to put one element to the correct position. In this case, we start from the last position. No, you can name it, or you can check, or can make it to the position that you want to find the correct the correct items to put there. So we start from the last element, and -1 is mean we try to put it in the last position here. We try to put to find the numbers that is suitable for the last position, the biggest value. Okay, so in order to do that, we do the for loop from the left. Okay, and put it make it move from the left to the right by compare and swap, swap until we can find the biggest value and put it there. Okay, now that is the review for the last section. Now this is your quiz. I want just to test. As you remember, we have I asked you to do the homework. Okay, so now what I want you to do, I want you to implement the algorithms in the descending order, in order to sort an array in a descending order. Okay, but I want you to do it from the right to the left. Okay, so try to modify the algorithm in such a way that you can sort the array in descending order, but you compare objects and move them from right to the left. Okay, so you got the quiz. That is your quiz. So I will type it here. So sort implement a function to sort a given array in to descending order, and the sorting is done for from the right to the left. Right to left, the one that I explained here is mean we try to compare and move things from the right to the left. Okay, so everyone, let's do it in 15 minutes. I hope that if you spend some time for your homework, that should be very easy for you. Okay, that is somehow the reward of working with the homework. Okay, so let's do it. I will make an assignment in Blackboard, and you can always do it and then submit it there. Okay. disagreement. The others, please try to react to the message, no? To let me know. Yeah, it's great. Okay. If you already finished the quiz, you can prepare for my question for you is this one. So my question is, when you think about purple socks algorithms, uh, what can be improved in the purple sock algorithms? Okay, that is the question. What can be improved in the purple sock algorithms? Think about that. After like 11, I will try to do it. Okay. Yeah, yeah. I need to have a concrete solution. Means what should I do concretely? Okay, I think that I think that time for the quiz. So I hope that all of you can finish it. Okay, thank you. So now we're back with the slide and the thing that we want. So here you see that we wanted to modify the purpose of all items. Okay. So people now let me go through the purpose of all items when we try to compute exactly the number of operations that we have to do for the purpose of. Okay, so you see that for the number of comparison in the purpose of, what we see is that every time we have to compare element to the remaining items. Okay, at the beginning that will be n minus 1, and after each iteration the number of computation is reduced by 1. Okay, so we have 1 minus 1 n minus 1 plus n minus 2 as the number of comparison for the second iteration, and so forth until we have only 2 elements and we compare one time only. Okay, for that, and you know they have a formula to find out the sum. So the sum will be n multiplied by n minus 1 divided by 2. Okay, that is the exact number of comparison we have to do for the purpose of algorithms. You know, it's quite a lot. So if for 10 elements we have the 45 comparison. Okay, so what we can say is easier about n squared divided by 2 is the number of comparison. Okay, and then so for the number of swap, okay, so we have the fewer number of swap than comparison because it depends on the data, of course. Okay, and in general what we can estimate, so let's say it will be half of the time we have to swap. So what we can say is that for the comparison we have n squared divided by 2, and for the number of swap we have n squared divided by 4. Okay, and you see in the worst case it means we have to swap every time we do. It's been in in which situation we have to have to swap for every single comparison. Which one? That is when we that's one why when we do it. This is when we have the in which situation every comparison result in one swap. Yeah, that will in the sorted, it mean in the reverse order. Okay, yeah, great, that's it. Then you know that's that thing, and again and again, just to remind you, for the complexity, if any big enough, we not really care about divide by 2 or divide by 4. In general, we can say that is n squared. So it's slow for sure. And the way that people can know whether or not given algorithm without going to detail, without analyzing all of the steps of the algorithms, you know that is easy for purpose of because it's quite simple. But for big algorithms, a complex algorithm is not easy. One hint is to just check the number of for loop that we have and the number of nested loop. Here we have 2 loops that nested in each other, so the complexity O(n squared). Okay, so that is one of the way that people can use to say estimate or to determine the complexity of the algorithms. Okay, of course you remember in purpose socks we do it n time for n element. For each element we have to compare for almost like all remaining items and do the swapping, so we have n squared for that. For each element we do n step, so we have n squared. Then just here the question for you, just to like recap everything. What is correct about purpose of? The others. Yeah, A for sure. Okay, and now just to clarify things, in A we have the comparing and swapping. Okay, of course this is not moving, but do you know the difference between swapping and copying? Is it the same? Why it's not? Are they the same? Swapping and copying, is it the same? No, because what? Because what? Because what is the difference between swapping and copying? Yeah, of course, that is the meaning. But in terms of operation, we have something else, no? Yeah, copying. Yeah, as the final result, we have the difference. Like we just have to think. But in terms of operation, you see that copy is just try to assign the value of in one cell to another. We have the copy and that's it. It's just one step. For the swapping, we have to do basically 3 operations. We put the value at the destination slot, put it in a temporary variable, and then we copy the value from the source to that destination, and then we copy the temporary value back to the source. So we have 3 steps, 3 operations. You know, it's been somehow we say it 3 times like more expensive in terms of operation than the copying. Okay, so that is the difference. Okay, at least of course the meaning is totally different. Okay, and now back to this one. Some of you are mentioned about say, hey, well, what is the difference? What we can improve? And you say that Thuận and Khang say, Thuận say, yeah, if we know that if for the first iteration, if we already started, we can stop the algorithm. Okay, we don't need to check it many times. Of course, there is one improvement we can do. That is that will help us to save some operation in the best case. Okay, normally in the best case we can improve the algorithms quite a lot. But what we should do is say on average, normally we will have to sort the array. Okay, the chance that we have sorted array is quite small. Okay, so yes, you can improve that, but let's think about something that is bigger, that is more, like have more impact than just like optimize for a specific situation. In this case, you see that we optimize for very good, the best situation that we can have is the what, or we say the best the sorted array. Okay, now think about the algorithm again. Okay, let back to this one. I think that is the thing that we can do or you can do later on when we have some algorithm at hand and people complain about the performance of the algorithm, and then you sit down and say, wait, well, what can we do? Okay, normally one hint for you is try to think about the invariance. It means the goal. of the algorithm, why we have to do this and that, and in detail what we want to do. Okay, I would try to open a Word file again so that you can see this. If you remember that we have some algorithm, I just put it like this one. The way that we do the sorting. Let's say we do it very briefly with this one. I will do the swapping from 89 and 58. So you know that I have it. And then next step we do it again. This one and this one. And this again we have this one and this one. And last one we have this and this one. Okay. And for the next step we will repeat that process to run for the array again. So we swap 28 and so forth. Okay. Okay. So now let's back to the this one. So do you remember what is our goal, our invariance for the algorithms? So you see that we try from the algorithm, we say we have here at the last position, and the goal of the first iteration is bring the biggest value to the correct position or the last position. Okay, and the way we do here is we try to compare. Okay, and then if it's not correct, we swap, and finally we swap again and again until we arrive at the last position. We have it. Okay, so you see that is the way that people solve too. But then sit down and think about that. Can we improve it somehow? So can we reduce some operation in this situation? Is it possible to somehow reduce the operation that we need to do in order to achieve what we want? What can we do? Yes, that is very good, Tom. That is what we really want. Okay. The goal of our comparison and swapping is that we just want to move the first element to the last position. That's it. That is our goal. Okay. And in this case, we compare and then we swap. But think about that. We swap it many times. But the final goal is just to bring the biggest item to the last position. Okay. That is good, Tom. And actually, that is the one that people did. And finally, we have a new algorithm. And we name it selection sort. Okay. And the idea is that now we try to reduce the number of swap with the same number of comparison. Okay. And you know that we want to, if we do the thing like for each iteration, instead of swapping n time, now we swap it one time only. And finally, number of swap we will have from n squared back to n. Okay, you see the difference, no? And here the comparison is still the same. That important when we deal with big data set in terms of swapping, no? We reduce quite a lot of time. Okay, and the swapping time will be more important than the comparison time. No, comparison is just one step, and swapping we need to do three operation, and we do many things in the memory. Of course, it takes some time. And here the selection sort algorithm, and have that now it's very clear for you. We start from the first element, let's say from the left, from the right, whatever. We scan all the elements in the array to find the smallest. In this case, it could be largest, whatever. It will be equivalent. The smallest item, and then swap it to the correct position. That's it. That is the selection sort. Okay. The idea: find the best. I mean the smallest or the biggest value. Put it in the first position. That's it. Okay. And Next step, second iteration. For the second last position, find the second largest number, put it there. That is the algorithms. And we do it again and again, just like the bubble sort, until we go through all of the position and we find the sorted item and put it there. That is what we want. Okay. So here again, I will show you the algorithms, the simulation to see, say, not on the way that we run it. We see now. You see, there is a lesson sort we go through. We don't need to swap every time we move, but we just try to find the max or the min value and then put it there. Okay, see, nearly sorted. Put it there. Put it there. Okay. Okay, and this one. Okay, so you see we reduce the number of swapping, obviously what we can see here. Okay, yep, that is the algorithms. Okay, and now you see for each iteration we have to make a comparison, but only one swap. Okay, and then here is the code. Okay, have a look at that code. Okay, everyone. So here's the code. I hope that you say now. See that we have two for loop as in the bubble sort. The code is a bit more complex. Means that we need to find the min or the max value here. We have the out is containing at the position that we want to find the items that suitable for that in the final position, means the min. If we sort it in increasing order, we start from 0, it means the min value there. Okay, and then we try to find the min like this. We do the for loop, means in and then if it's smaller we put it min. It is the index. Okay, we just put it in index, and then we do swap. Finally we swap the value at index min to the value at index out. Okay, that's it. Okay, here there is one question and one thing that I would note for you. This one, you see that this is out. Okay, there is one thing that is small, but I want to ask you. You see this value, out plus 1. My question, can I just start from 0 instead of 1 or 1 if you want, instead of out plus 1? Means, is it this one is just the way to optimize thing, or can I just put it like this? We start from 0 or start from 1 if you want. Is it possible to do that? The others, yes or no? Can we start from 0 there? The other, yes or no? Think about that. The others, everyone? The others, try to tell me. We have 50 of you here. Everyone, come on. Do it. Just tell me. Great. Thank you. My answer is no. Okay. Now, some of you please try to tell us or give us one concrete example why is no. Why we have to do it at r plus 1? It's very good, Thông. Everyone, have a look at this. Let's say I have my number. Yeah, I can change for sure, but is it just start from 0 is like the way to improve the algorithm somehow? My answer is no. We have to start from r plus 1. Okay, I just bring back this one. Let's say I have my number. I have my array. Okay. For the first iteration, what we try to do is we try to find the min. Okay. Find the min value to put it in that position. Okay. Let's say I will put it here. I will try to find some value to give it to that position. So I go through from 0 is the index here 0 1 2 3 4. Okay, so I start from 0. I go through the array and I find that 1 is the smallest value and in next 4, and finally I will swap 1 with 0. The thing we have is this one as the final result of the first step. Okay, and now the next step, the next iteration, I try to find the value to put it in the second position. Now it is very important. If we start from index 0 again and we try to find the min, what happened? What happened is that we will conclude that 1 is our min again for sure, because 1 is the smallest value in the array. We found it last time. Okay, and if we run the find min algorithm again for the second time, 1 should be the min again for sure. Okay, but what we want for the next iteration, what we want? What do we want for the second iteration? We want to find the second largest, second smallest value in the array. Okay, that should be 18. Okay, you see? Everyone else got it? We have to start from 1 because we should ignore the smallest value from our array, our checking range, so that we can find the second smallest value. Got it, everyone? And the others? The others, is it clear? Is it clear why we have to start from r plus 1? That is very small thing, but it's like the key things for this algorithm, So we are working on algorithm that is very important to check on every single detail of the code. Okay, people do it for the purpose. Okay, it is not random. Okay, yeah, that is good. Now I think I hope that is clear for you. And now what we want for you to just somehow practice a bit. If we're not really really comfortable with the the sorting algorithms. Just sorry, I should jump. Okay. Now everyone, do it again. So I want you to do this, to do the sorting manually again for this array, first array. Okay. To see the difference, everyone. So let's do it. Take some time to do it. Okay. So it helps you to get familiar with the algorithms. Okay, and do it like when you finish. Okay, sort this array manually means put it in the right order following the algorithms. I may repeat this one for you. So now just this one, 2, 4. And sorry, I need to move it again so that we can have the algorithms that you want. So here's the array, and that's what we want. Okay. So please do it. Cute. The question is when sort the array manually using selection sort. Yeah, of course. Okay. So everyone, the others, can you finish it? It's quite like it's quite efficient in terms of operation that we had to do. You know? Find, scan, find the max, min, swap. That's it. Okay. That is the selection sort. Is it clear, everyone? Do you have any other question on this selection sort? Okay. And then if you don't have any question, let's try to see this. Okay, as the algorithm is the ON square for the reason you know, because we had two for loop. Okay, so that is ON square because we had two for loop, means that yeah, we need some time to do the sorting. Okay, and the number of comparison for the bubble sort, you see that it is the same as the bubble sort because we have to compare every time. The n squared divided by 2, and the number of scrap for sure would be n. And it's faster than bubble sorts for that reason. Okay, so you see that there's just the thing is, it's just one concrete example why we have two algorithms that have the same complexity O n square, but one algorithm is faster than the other in the running time. Okay, because the number of operation we have to do is smaller. In this case, smaller number of swap. Okay, now the question for you. What is the answer? That is the correct option is that is the answer is B. This one. The minimum keys is repeatedly discovered. Yeah, accumulated on the right or on the left, it depends on the ascending or descending order. Okay, but in the invariant. What is true for the sorting or this sorting algorithm is we try to find the mean values. Okay. So the best option there is B. The idea for the algorithms to find the mean or to find the max value. Okay. Okay, everyone. Okay. Now move on. Okay, clear. Now we try to move to the next algorithms that insertion sort. Okay. Now think about the. Of course, it's not easy anymore. Think about the sorting algorithms again. We have this one. The way that we try to optimize, to improve the algorithms based on the bubble sort and insertion sort is quite good. Now people try to sort the algorithm in the. We try to improve, not really improve, but try to sort the algorithms, sort the array differently. Okay, there's many ideas how to do it, but there's one idea that have us just based on two basic operations, compare and swapping. But I know that it's not easy. But can you imagine or can you propose some algorithm, some way to reduce the number of comparison in this case? So we see we have two things. This somehow like computer science means we will try to optimize the algorithm by look at the number, the operation that we have to do. So last time we have a lot of comparison and swap. People reduce the number of comparison. Number of swap by finding the max. Okay, that is good. Then we have new algorithms like selection sort. Now imagine that we have another like a parameter that we can optimize or tuning, that is the comparison. Do you think that we can reduce the number of comparison for each iteration? So we don't need to compare everything. Is it possible that way? Normally when we do the research, it's not like we should try somehow, not just give up quite easy, yeah, no, that's it. Yeah, you have the idea of binary search, how to do it. And Thịnh, you have any idea? Yes, let's tell us a bit more detail. It's a very good remark from Khang. You say that we can apply binary search somehow. But think about binary search. How can we reduce or ignore items in binary search? I'm not really get what you want. What you mean by what do you mean by using I not array I index? How we can compare using index? We have to look at the concrete value in the array to know whether or not it's bigger or smaller than the others. Now let's back to the idea of kênh. It's good, kênh. It's good. In binary search, think about that. How people can ignore the half of the array in binary search. Because what? Because in binary search, in a sorted array, or everything on the side, yeah. Just back to the idea of binary search. Binary search, we have some increasing order, and we compare it with this number, okay, in the middle. If our x is bigger than this guy, means that we don't need to care about the remaining, and we can skip them. Okay, so we don't need to compare for each item here to check anymore, because we know for sure that everything on the left side of this guy is smaller than this. Okay. 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 Thịnh and Minh, you try to tell us something, but anyway, then we have to compare to others. Now, just don't check anything else. I will show you the insertion sort. Okay. This is based on the idea, based on the observation that Thịnh had mentioned. It's good. Kênh. Okay. In many cases, this insertion sort is the best of the simplest sorting algorithms. In the means the best of the three algorithms. Okay. Anyway, it is n square for the complexity. Okay. But when people compare the running time or execution time, it is 2 times faster than the bubble sort. Okay. And it is faster than the selection sort. Okay. In most of the situation, that is very good. Of course, we have to make it a bit more complex. Now let's try. Let's think about that and have a look at the insertion sort and see. Sometimes we can use it as the final stage. This means we combine with another algorithm. We will see it later. Now, the idea for the insertion sort is this one. People try somehow to virtually divide the array into 2 parts. This one is sorted increasing order. Okay. This one is not sorted. Okay. And what they try to do, they try to insert this guy to this sorted part. Okay. That is the idea. Okay. And now try to go a bit more detail and see. Okay. So we have three notions here. This is partially sorted, this is marked item, and this is unsorted array. So if I write it like this, okay. Okay, you see that now they try to make that thing. The idea is we try to insert, and of course insert somehow we shift things to the left, to the right, to move it to the right position. Okay, and then we put the item in the correct position. So we insert new item to this one, and after that iteration, we have one more item in the partially sorted subarray. This one means for each iteration, we have one more item in partially sorted. And if the partially sorted subarray reach a contain n elements, means that that will be the whole array, and we finish. Okay, so we do n step. Each step we try to make the partially sorted array bigger and bigger until it reach the whole array. That is the idea. Okay, the way that we implement it, we will check it later. But now there's something I want to do it. This is what we do. Oh, sorry. I think I go too fast for you. Now, sorry. I will do it better. The idea, sorry, this one. Now, we have here. Okay. Now we want to insert this mark player to the sorted somehow. Let's say sorted array or partially sorted. So what we can leverage from there is that do you agree that if it in the increasing order already? So in order to find the, let's say the suitable position for this guy, what we can do, just for example, we will go from step by step until we reach some guy that is smaller. This guy is that high. Let's say this is that high. Okay, it's cut it here somehow. And if we found some guys we go from the right to the left until we reach some guy that is smaller than my mark player or items, then I can stop. Because I know that if I continue to go to the left, I will get something is smaller and smaller. Okay, know that everything from here, from that position to the left is smaller than my objects or my items. Then I can insert my players here. Okay, because it's sorted. We have something. We know something. We know that everything on the left of that guys will be smaller than my data. So I don't need to compare anything else. I just stop there and I know that my object should be here. Is it clear, everyone? Okay, let's talk about shifting and things later on. But now let's think about that. Okay. Okay. Now, to explain the thing. Now think about the number of comparison. Do we reduce the number of comparison? Do we reduce the number of comparison? Okay. So that is the goal. We reduce the number of comparison, and then let's check what happened. Okay. Now the implementation of these algorithms. Okay, I will show you. Let's run it first. Run it first. Okay, to see what happened. Up. Wow. Oh, sorry, I pressed something wrong. Sorry. Up. Okay, here we are. Now let's see the running in action to see what can we save. Now for the insertion sort. Okay, the idea is they will try to to run the algorithms. At the beginning, they will say the sorted, partially sorted array we have one element only at the beginning. Okay, we try to insert the first element to the array of one element. Okay, and then we put it there. And after that, we have the array, the partially sorted array with two elements. We try to insert the third element to that array. Okay, and so forth. That is the idea for the insertion sort. We try to increase the size of the partially sorted array one by one. Okay. Now let's check what they did or what they do. Okay. Okay. Again, at the beginning, you see, at the beginning they don't need to go through everything because they just work with the two elements. Okay. In the second time, they work with three elements, and third time work with four elements, and so forth. Okay. You see, just the number of operations. Okay, and here they try to sort from the top, and the number of thing and the number of operation and the number of position that we have to shift. Then look at that. In the range of the size of the partially sorted element only. We do not shift everything. We shift what we need to do. You see? Okay. Okay. And now what we try to do is as the invariant of the algorithms, and then for every iteration, the partially ordered list is larger and larger for each iteration. Okay. Okay, so we have one new item to put in the partially sorted array, and until all the unsorted items have been inserted, okay, so we're going to insert and sort. Now, I will look at the code later on. Maybe I will just do it here for you to see the difference. Okay, now I have my array. Okay, what we do, so I have this is my sorted array, subarray, a partially sorted array. Okay, so my first task is to make this one, to move this guy to the sorted array. So just two numbers, I compare, and I know that it will be the last. This is quite straightforward. Okay, and now I need to do this. What I do, let's say let's do like this. Now what people do is we try to show you how we do the shifting. Okay, so 29, what we do, we need one extra variable. Let's say my 10. Okay, I put it 29. Okay, so I compare this number, the first element in the partially ordered array from the right, compare with 29. Okay, so this guy is bigger than my number. What I do, I will not swap, but I just copy. Again, you know the difference between copy and swapping, no? Just copy and put it here. Okay, and then next step, I check this one. I compare 58 with 29. This one is still bigger than my numbers. I copy it here. Okay, so that we have, and then I reach the end of the array, so nothing else. So I put my numbers here. I copy the 10 here. Okay, so I have my second, my next sorted, right? I move to this guy. Okay, so now again, what we do, we compare 40. I put 40 here. I compare 40 with this guy. This guy bigger than 40. I put this guy. Copy it over there. I compare 58 with 40. It's still bigger. I copy it here. Now I compare 29 with 40. 29 is smaller than 40. So we know that everything from this guy to the left will be smaller. So I can stop and put it here without compare any others on the left. Of course, here is just one on the second. Okay. So I just try to modify this number so that you can see the value of this. Let's say I have it like 55. Okay. Now you see that we want to compare 55. We want to insert 55 to the array. So I put the 55 in the temporary. Okay. And see this guy. Now I compare 80 and 55. 89 bigger. 58 is still bigger. Copy it here. And now 40 is smaller than 55. I don't need to check anything. Don't need to compare anything on the left of 40. I can stop here and then put it there. Okay. So you see the number of comparison and the number of swap can be reduced. Can be reduced because we have the order in the partially sorted array. That is the insertion sort. Okay. Now is it clear, everyone? Yeah, you see the algorithms. Of course, when you think about that, they help us to reduce the number of comparison and of course the number of swapping. Okay, so let's think about that and let's take the 20-minute break for your lunch, or if you don't have it yet, and we're back with some hand-on like example, and we try to run the code. Okay, so try to put it in your head and then digest it with your lunch. Okay. Okay then. See you in 20 minutes. Okay. 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 Hello everyone. So welcome back. So now of that. Okay. So we have this exercise. Now I want you to just play a bit with the instructions on your own. Okay. So that you. Okay. I will try to show you this one. And now this is the instructions of algorithms. Okay. So I want you to do it. This one. What? So I want you to do the sorting for new array, okay, using the algorithms. Maybe if you want, you can do it manually, but at least try to do it so that you can feel the, uh, the difference. Okay, so everyone take some time to do the to run the instruction sort algorithms here with this number. Okay. It's almost like the one that I showed you. Okay, so please do it. Run the instruction sorts on the array. Like when you finish. Okay, so try to do it on your own, please. Manually or using the algorithms. It's up to you. No, just see the code and run the code for this instruction or for the array, or if you want to do it manually just to make sense of the algorithms. Finished. Lê Thành. You got it. Okay, the others, please do it manually, and when you finish, like the message to let me know. Okay. Yeah, the others, please like the message when you finish. Everyone. Thank you. Kang, what do you have? First run. First run we what? Okay. What? Kang, what's wrong with your items? Why first? The result, the first run, why we put 30 in the in the third position. Okay. The first run should be 5 at the first position and 30 as the second position. Okay. We will not jump. We just do step by step. Okay. No. I will not use the keyboard swap, but for the first pair, yeah, we copy 30 to the copy 5 for the first step. I copy 5 to the temporary variables now, and then I compare 5 with 30. It's 30 bigger. I copy 30 there, and this I put 5. The result of the first step. Okay, and the second step we try to insert 19 to the array of 2 elements like this. Minh, we have 5. Okay, yes, that is the thing. Yeah, it's almost like that. Yeah, that's it, Minh. I just repeat my message here, like when you finish. The others, please react. Tell me that you can finish with the insertion songs manually. Great, thank you. It's good. Thank you. Thank you. The others, do you have any problem with that? It should be the others. Okay. So again and again, I ask you, please react to my message so that I can know like your progress. Okay. And if you have problem, please be active. Try to send me a message. If you want, you can send me a direct message, but it's not recommend that. Try to participate in the chat box in a class like this. Ask me a question. Okay. If you say there's something strange, or I don't know how to do the second iteration, whatever you have, tell me. Okay. Otherwise, I will assume that you are okay too, and I will move on after some time. Okay. So please be active. Okay. Otherwise, now my question for you. First, what does it mean by this? What is it? Why we need to do this checking? What is it? Why we have to check that in the bigger than 0? Why, everyone? That's what we want. Yeah, to have us to know whether or not we are we reached the beginning of the array or not. No. Okay, that's the first question. Second question. Is it possible to run these algorithms for the descending array, to sort the array in the descending order? Is it possible? It means after we update. Of course, yes. An algorithm should be able to sort it in some order. Now, time to practice, everyone. My question for you. Now, I want, as you remember, like we have this array, these algorithms, these current algorithms. We try to have something that in increasing order, and this the first part. Then and this is some numbers in not in a good order, and when we try to take the element from the right side, try to insert it to this array. No, that is the way we do. We try to have partially sorted array, and we have something unsorted when we try to insert it there. Okay, and you see the way that we do it from the left to the right. Okay, we build up the partially sorted array from the left, and I put a thing from the right to the left side. Okay, now I want you to modify the code, it means this code, in such a way that we can sort the array in descending order. Okay, and I want you to do it in the opposite direction, means this one. We want to build up the sorted part on the right and on the unsorted part on the left. Okay, and insert things from here to here. Do you got the idea? So this is the in-class question. So in-class exercise. What is it? Is implement function to do the insertion sort for descending array from, let's say, I would say from right to left. And of course, my text is not correctly describe the situation, but I just describe briefly like that. In right to left means that we build the partially sorted array on the right, okay, and we try to move things from the left to the right, okay. I hope that you get the idea. Okay, so everyone, please modify the code here, okay, and tell me how. Think about that. It's just necessary to have you to play with the code, okay. So of course I can put it like there's some key part, and everyone think about that. And again, this is algorithm. You have to think about that. You have to practice. You have to do the exercise in order to learn. Okay. So, and again, like when you finish. Everyone do it, please. Okay. Okay. Sure. So to explain the code. Okay. So we do the for loop. We start from R, it means the index of the. I will try to see to show it here, array. Okay. So we have many elements. Okay. So we start from out, it means we start from here. What out means that this is an item that we want to insert to the partially sorted part. It means we want to insert this one to the one on the left. Okay. Okay. And then what we do, we store this value to a temporary variable t. Okay. And we store the value of a out. We put it here. We copy it. Copy the value here to this t. Okay. And we say in is just the index. We start from out here. Okay, we start to copy here, and we do the while loop. While loop is that we check if in the bigger than 0 or not. Yes, it's true. And then we say we compare a this one and the one that before that. Okay, we compare these two numbers. Okay, this one and this one to see whether or not this one is bigger than my numbers. This one is bigger than my numbers, mean that say it is in increasing order. It's an increasing order like this. Okay, and I want to insert my item that high. Okay, so what happened? I would compare this element here. This is bigger than my number, so I will copy. I will say a in equal a and plus minus 1 is I copy the value here, this tag, to this position. Okay, and then I move my index to that position. I move my index here. Okay, I repeat it again. I check if I reach the beginning or not, and then I check whether or not the new items here on the left again, is it bigger or equal to my variable in the temporary variables? If it is still bigger than my item that I want to insert to the array, I will copy it again. I will copy it here. Okay. And next time, let's say I have something else that is here, that is not 0, but the value here is smaller. It's smaller than my value at the beginning. I know that for that moment, everything from the left of that part will be smaller than my numbers. Okay, so what I do, I will copy my value there. I copy my value to the slot I compare. Okay, I copy my value, and this is the thing. Okay, that is the right position. Okay, the algorithm is the copy. So the algorithm try to do is, instead of doing shifting, now what I do the compare, and every time is yes, I just copy it one by one. Okay, until I find they in the same time find the position and move everyone to the right in the same time. Okay, that is the idea. That's it, the algorithm. Okay, Minh, is it better? Great. Now the others. Try to modify the algorithms as in class exercise. That I think that will help you to understand the algorithm better. Okay. Hello? Can you finish it? Think about that. What should we do? What should we do, everyone? What we try to do is we try to modify this one. Huh? Okay, great. So what we try with here in this algorithms, the hour is from 1. It means we start from the left. Now we should start from the right. No? We should say it should be. We should modify this somehow. So the hour should be n element minus 2. This means my array like this. Let's say here. Okay. I should consider this. This is sorted. This is sorted. I start from here. Okay. I start from here. Okay. And then I just copy. And what I do, I do the while loop. I do the while loop instead of do it from here back to the left. Now we have from this position to the right. Okay. So here the ascending is if a in is still smaller than n minus 1. Okay. It should be n minus 1. Okay. And the a what? A in plus 1 is bigger than my number. In here, if the one on my right is bigger than my number, sorry, not bigger, is the one on my right is bigger, yes, it's bigger, like this one is bigger, I will move it to the left. Okay. Until I find something that is smaller than my number, I stop there, just copy. Okay. So what I do, if a in, it means this one is bigger than my temp, I copy it to the right. So I have to modify this one to be something else. It means in plus 1. Okay. And this one is plus 1. Okay. And after I'm done with that, I move in to the right. So plus plus. It's like that. Of course, I strongly recommend you to at home try to do it, implement it in your computer so that you can test. Okay, everyone. So now I think that's it for the exercise. Okay, if you still have a question, you can always ask me. Okay. Now, back to the original version. You see that we start from item. We have 8 hour is a market item, and we want to move it to the temp, and we have sorted, and the algorithm is the O n square. Because each step we do for all elements, we have to try to insert into existing. But if we want to go to precise value, we have this. For the first pass of the algorithms, the maximum number comparison is 1. Do you agree? For the second pass, the max is 2. The key thing is the max. Last time, for previous 2 algorithms, we always have to compare to all the item in the array. Let's say n minus 1, n minus 2 for each iteration. But now, what we do is we try to have it. We start from 1 and 2, and this is the maximum. It means in the vast chance that we have to compare to all elements one by one. Okay. Otherwise, we have a great chance that we can stop in the middle, somewhere in the middle of the the sorted array because my numbers is somewhere here. Okay. So we say this is the max. Okay. By the way, where we have max number comparison, it's been in which situation for all the paths we have to compare the max and minus one comparison for all of the iteration. It's been when we reach the max number of comparison. When? Everyone? When do we have the max? That is where we hello. Again, yes, reverse order. Let's say every time we have to insert, we have to go through all of the elements to compare, and the last the position we have to insert is the last position here. Okay, we get smaller and smaller. This means if we put it in inverse direction, so we have the max. Okay. Yep. And you see that the number of comparison again is this one for the max. Okay. On average, we can say it divided by 2. On average, half of the time we have to go through all of them. Half of the time we don't have to compare anything. So by chance, we say it divided by 2. Okay. So you see that we can reduce the number of comparison, let's say on average, by half of the time. For the insertion of the number of operation, so we do a lot of copy operation. Okay, but you see the way that we copy, let's say copy is not swapping. We have one copy only, one operation only for the copy, not three operation. Okay, and is it good? Because we reduce the number of operation. We don't have to copy and swap, things like that. Okay. But again, copy is not time consuming as swapping for sure. And you see, for the shifting, the idea of shifting is not the shifting like we have in the array, insert element to array. If we have long array here with many things we don't know, so we don't care. We should shift inside the thing that we have. Okay, we do the shifting in that part only. So the number of copy is still not that big. When we do it on the random data, so the insertion sort is twice as fast as the buffer sort, or faster than the insertion sort. We see the way, because we have reduced number of copy and number of comparison. Okay, and in general, it's still n squared. For nearly sorted, it's very good. Okay, and for unsorted, it means reverse order. I say is not better than buffer sort. Okay, for that reason, we have the same complexity. Okay, and last one. For insertion sorts, what does it mean by this notion? Partially sorted means what? The answer is what? The answer is D. Here, when we say already sorted, means that in final position. No. Okay, for sure we do the shifting later on because we increase. Final sorting position, no. Okay, some of them are sorted is not really true. So the answer is D. Okay. Group of items are sorted among them. It means partially sorted. Okay. The others need to be inserted into it. That's it. Okay. That is why we have insertion sort. Okay, everyone. Now the last topics that I want to mention. So for the sorting algorithm in general, all of the sorting algorithm it should be able to use for objects. It means a list of students, list of employee, or list of car, whatever you have. Okay, because we are not only work with numbers. Sure. Here the difference is that every time we access the element, instead of get the numbers that we can apply the comparison directly, we can we now get out of an object. When we get objects, we get the last name, first name, or whatever, and we can use operation and compare something. Okay, compare with the 10. That is the sorting objects. Okay, so it means that all of these sorting algorithms can be applied to sort array of objects of custom object like student, class, car, price, ticket, whatever you have. Okay, and here is the homework for you. Now you know that if we working with object, this is not only we have many fields of data for one object. Let's say student. We have their birth, we have name, we have GPA, we have many other things. Now let's say if I want to sort like in Excel, if you know it, I want to sort my array by your GPA, by GPA of the student. Okay. Then what happens is if they have the same GPA, I want to sort them by the day of birth. Okay, day of birth. So you see that we have two criteria. Of course, we can have multiple criteria, means multiple level of comparison. My question, my homework for you is, how can we implement this one? How can we sort a set of objects with multiple criteria, at least two here? Okay, is it clear? This is your homework. Think about that, how to sort objects with multiple criteria. Okay, everyone, so that's it for today for the sorting algorithms, and there is the homework. Do you have any question? Otherwise, that's it, everyone. Thank you for participant, and of course I strongly appreciate your participation in very active in reaction and post your solution to the chat box. Thank you very much. That's it for today. Goodbye, everyone. Bye bye.